While reviewing many accident investigation reports, I noticed that the pilots and the accident investigators were not aware of a very important restriction that comes with a minimum control speed VMC. I also noticed that the VMC definition was copied straight out of aviation regulations that are for the design of airplanes and not for their operational use. The consequence was that mishap pilots maneuvered their airplanes at airspeeds as low as VMC while an engine was inoperative and lost control and in many cases also their lives. I am Harry Horlings. I'm a graduate of the US Air Force Test Pilot School in 1985. I'll briefly explain a few subjects that all have to do with preventing accidents after engine failure. I'll do that exclusively using books of leading universities and experimental test pilot schools and not in accordance with publications by whoever, not even including airplane flying handbooks issued by aviation authorities. I'll briefly explain airplane control after engine failure and the truth about minimum control speed VMC. In order to do that, I'll explain a little on tail design and the resulting constraints for flight with one engine inoperative. Then I'll talk about the effect of bank angle and weight on the minimum control speed. I'll also explain why pilots don't have to know about the critical engine and how VMC is determined during flight testing. I'll answer the question why VMC definitions in airplane flight manuals, flying handbooks and textbooks are deficient and lead to catastrophic accidents. And finally, I'll discuss the two accidents you have seen in greater detail and present some do's and don'ts for staying alive when an engine is inoperative. This video might save your life already tomorrow. Airplane control after engine failure. Federal Aviation Regulations and EASA Certification Specifications 23 and 25, paragraph 149 and equivalent, require a minimum control speed VMC. VMC is the calibrated airspeed at which, when the critical engine is suddenly made inoperative, it is possible to maintain control of the airplane with that engine still inoperative and thereafter maintain straight flight at the same speed with an angle of bank of not more than 5 degrees. There is two requirements for the magnitude of VMC in this regulation. The first is maintain control, that is recover following a sudden failure, and number two is maintain straight flight during the remainder of the flight while an engine is inoperative. Please notice that there is absolutely no requirement for maintaining control during turns at airspeeds as low as VMC, only for straight flight. VMCA for minimum control speed in the air will be used in this presentation rather than VMC. VMCA is more commonly used today to distinguish between other VMCs. The VMCA of an airplane is published in the limitations section of its flight manual. VMCA is also presented with a red radial line on the airspeed indicator or on equivalent electronic displays or on a placard in clear view of the pilot and as close as possible to the airspeed indicator for heavier and turbine-powered Part 23 airplanes. The blue line speed is VYSE, the airspeed for maximum rate of climb with a single engine. So, VMCA must be an important limitation. But what exactly is VMCA? Let's go back to its origin. Directional control after engine failure. Engine failure causes the airplane to yaw into the failed engine. A rudder side force is and stays required to counteract the thrust-induced yawing moment. This rudder side force also causes displacement to the dead engine side, hence a side slip starts to increase. This increasing side slip results in an increasing opposite side force due to side slip caused by the fuselage and the vertical tail. The rudder needs to overcome this side force too, increasing the required rudder deflection. When a balance of side forces is achieved, the side slip increases no more. there is a minimum airspeed to generate the required side force for balancing the thrust yawing moment and the side force due to side slip. We'll get to that later. Lateral control after engine failure. A side effect of yawing after engine failure is rolling due to the increased speed of the good wing and less propulsive lift of the wing section behind the propeller and less lift of the affected wing because the section of the wing is blanked from the wind by the fuselage due to the side slip. So, aileron deflection is required to recover and to maintain the desired bank angle. The VMCA requirement in the aviation regulation require the rudder and ailerons to be large enough for counteracting the yawing and rolling moments at an airspeed as low as VMCA. When, after engine failure, the wings are kept level, a side slip cannot be avoided. However, side slip causes drag, and drag degrades the climb performance. Especially when an engine fails immediately after liftoff, you need maximum available climb performance, and hence you would select maximum thrust on a good engine and you would like minimum drag by reducing the side slip angle. This can easily be achieved, as I will show you later. The rudder and the ailerons are the only aerodynamic control surfaces available to the pilot for maintaining an equilibrium, a balance of forces and moments after engine failure. A few words on tail design. Aviation regulations require for Part 23 airplanes a VMCA to be less than or equal to 1.2 vstall, so the tail cannot be made too small. The takeoff speed must be greater than or equal to 1.05 Vmca, a 5% safety margin above the minimum control speed. Operators want a low takeoff speed, that is a low Vmca, to be able to operate from shorter runways or with a higher payload from longer runways, resulting in a large tail. A large vertical tail does decrease Vmca, but increases both weight and manufacturing cost, which is not liked very much. The regulations offer one more option for a smaller tail, a lower Vmca and a zero side slip angle, which is a small bank angle. The figure shows a balance of side forces of rudder and side slip as mentioned before. With the wings level, a side slip cannot be avoided. Of course, there are many more forces and moments acting on the airplane, but these are the most important ones. When banking, a component of the weight times the sine of the bank angle phi, generates a side force in the center of gravity during straight flight. So this bank angle adds a side force, in this example to the right, decreasing the side slip. The VMC definition in aviation regulations allow the tail design engineer to use maximum 5 degrees of bank, which is of course into the good engine for the balance of forces. A larger bank angle increases the side force to a value higher than the rudder side force, increasing the side slip to the same side, which might cause the vertical tail to stall. This side force due to bank angle replaced the side force due to side slip, hence the drag can become the lowest possible. Remember, side slip angle and therewith the drag varies with bank angle when one engine is inoperative. The previous slide showed the decrease of side slip, that is decrease of drag with a small bank angle. This bank angle has also effect on the minimum control speed. The design engineer calculates this graph during sizing the vertical tail of this sample airplane. The graph shows VMCA and side slip versus bank angle when the left engine, number 1, is inoperative. When the wings are level, VMCA is calculated to be 120 knots and the side slip is 14 degrees, which means a lot of drag. For zero side slip, that is minimum drag, the bank angle needed is 4 degrees. VMCA will then be 95 knots. This is the design VMCA of the airplane that will be verified during flight tests. This VMCA is only valid if the bank angle is 4 degrees. This blue line shows the actual VMCA, being the VMCA that the pilot would experience in flight for changing bank angles. The actual VMCA increases when the bank angle is smaller or larger than the favorable 4 degrees bank angle for this sample airplane. If the indicated airspeed is lower than the actual VMCA, the shaded area, the control will be lost at maximum thrust. Dr. Jan Roskam of the Kansas University wrote in his airplane design book on tail design, the VMCA and side slip are tied together by bank angle. This graph shows just that. Remember, both VMCA and side slip, that is drag, increase if a small bank angle away from the inoperative engine is not maintained. The banking is to the same side as the leg pressure on the rudder pedal. The pilot controls the actual VMCA and the remaining performance with rudder, ailerons and the throttle, the magnitude of the asymmetrical thrust. If the rudder is not up to maximum for maintaining the heading, we also call that a partial rudder, a higher airspeed is required. The actual VMCA is higher. If the ailerons are not up to maximum to prevent rolling, a higher airspeed is required. The actual VMCA will be higher. If the airplane keeps yawing and or rolling despite maximum rudder and or aileron, the only option for the pilot to prevent the loss of control is to reduce the thrust just a little. Then the asymmetrical thrust is lower and less rudder is required to counteract. The actual VMCA will be lower. As soon as control is re-established and 5 degrees of bank into the good engine is attained, thrust can be increased again to maximum. The effect of bank angle and weight on VMCA. Lockheed C-130 pilots will recognize this graph. A similar one is in the performance manual on page 318. This graph shows the actual VMCA as both weight and bank angle are changed. This graph shows the effect of side force, weight times the sine of the bank angle for several bank angles. Shown is the 3 degrees away from the inoperative engine. I will discuss this one next. Shown here, the green line is the wings level. A straight line because the sine of 0 degrees is 0. Weight has no effect. As an example, 5 degrees of bank into the inoperative engine and 10 degrees into the inoperative engine. A low VMCA is safest, so for lowest overall VMCA, choose the bottom line, bank 3 degrees away from the inoperative engine for this sample airplane. For this bank angle, VMCA is lowest at high weight, but increases along this brown line as the gross weight is lower. We don't want a VMCA for every possible weight. It would mean too much test data, would be too complex to look up VMCA for the right weight, and would be prone to failures. A VMCA at low weight is highest, is worst case. In other words, this VMCA is safe for any weight, provided the bank angle is 3 degrees away from the inoperative engine for this airplane. This is the VMCA that will be published in the flight manual, and that is valid for all weights. VMCA wings level is 24 knots higher, which is less safe at low airspeeds, and in addition, wings level also comes with a considerable side slip, as was shown before as well. Conclusion from the graphs shown. The actual VMCA, that is the VMCA that the pilot would experience in flight, varies considerably with bank angle and weight and is definitely not a constant value. The pilot controls the actual VMCA with bank angle, rudder and thrust settings, and with prop feathering if that is manual. The standardized VMCA presented in flight manuals is always safe, but valid only if the bank angle is the same as used for designing the vertical tail while the thrust setting is high and the rudder is maximum. That is, during straight flight only. Any other bank angle increases the actual VMCA. The bank angle for the published VMCA to be valid is not yet presented with VMCA data in flight manuals, although some manufacturers present a bank angle for zero drag at the blue line VYSE in performance tables. For pilots to keep in mind, if the small bank angle is not being maintained, the drag is not minimum. Climb performance is less than would be available. The actual VMCA is higher than the redlined or placarded VMCA. During turns to either side at maximum thrust and too low a speed, loss of performance will and loss of control might also occur by definition. The vertical tail is not large enough for turning at airspeeds as low as VMCA and at high asymmetrical thrust, but is only large enough for straight flight, which was the requirement in the VMC regulations as I showed you. Even at the higher blue line speed VYSE, a small bank angle, usually 2 to 3 degrees, is still required for maximum climb performance or for preventing the airplane from drifting down during cruising while one engine is inoperative. We now get to the critical engine. Failure of any engine results in its own VMCA because the thrust is asymmetrical and rudder, hence a minimum airspeed, is required to counteract. Failure of the critical engine results in the largest thrust yawing moment because of P factor, that is the shift of the propulsion factor in the propeller disc when the angle of attack increases due to decreasing airspeed, and hence a failed critical engine yields a VMCA that is a few knots higher than the VMCA would be after failure of any other engine. So the critical engine is the worst case engine for the magnitude of VMCA, and therefore the critical engine is assumed inoperative for designing, for sizing the vertical tail, and is made inoperative during flight testing to determine the VMCA. Hence, the effect of the failure of the critical engine is included in VMCA. VMCA after failure of the critical engine is not higher, as is written in many publications. No, the VMCA, the actual VMCA after failure of any other engine, is lower, which is safer. The VMCA published in flight manuals applies after failure of any of the engines though, critical or non-critical. Only one VMCA is published. This is safe, provided a favorable bank angle is being maintained. There is no separate emergency procedure for a critical engine failure. No requirement for analyzing the criticality of a failed engine in the cockpit after engine failure. Critical does therefore not belong in the definition of VMCA in an airplane flight manual, nor in emergency procedures and in textbooks. It's for tail sizing and defining VMCA flight test conditions only, in accordance with the Aviation Regulations 23 and 25. If critical engine is mentioned, then the other factors that affect even VMCA and even more, like bank angle and weight, should be mentioned in the definition as well. But you won't see this. It's of no use. Pilots don't need to know about the critical engine unless one of the engine drives a pump for rudder boosting. This can be the other engine that the engine that would be considered the critical engine. Talking about surviving and critical engine failure is for nitwits, not for knowledgeable pilots and accident investigators. That is from now on. Many more factors have influence on VMCA. See my papers. In general, anything that affects the thrust or drag symmetry, that is, for which the balance of forces and moments acting on the airplane changes, has influence on VMCA. A few examples. An idling engine not set for zero drag. The drag asymmetry is increased and VMCA will be higher. A cargo hatch that opens in flight increases the asymmetrical drag, which affects VMCA. This is the worst if on the dead engine side. The transfer of fuel and or relocating passengers to the good engine side shifts the center of gravity laterally. The thrust moment arm of the asymmetrical thrust is smaller and actual VMCA is lower, which is safer. Increased engine thrust rating or new, more powerful propellers will result in a higher VMCA. A camera installed for fun, just for fun, on a wingtip affects the asymmetrical drag and therewith VMCA. Flight testing to determine VMCA. All factors that have influence on VMCA are at their worst case value. Low weight, center of gravity aft and into the inoperative engine, etc. because this results in the highest, the worst case VMCA that a pilot would ever experience in flight and is therefore safe for publishing in the airplane flight manual. Tests are conducted at a safe altitude of 5,000 feet at least and begin at an airspeed higher than the expected VMCA. For new airplanes, we even have parachutes in the seats. The fuel to the critical engine is cut. The propeller, if applicable, feathers if automatic, otherwise will be windmilling. The opposite engine is set at maximum thrust. Both are also worst cases. Then the airspeed is slowly decreased at a rate of 1 knot per second, while increasing the rudder and aileron to maintain straight flight until the heading or bank angle can no longer be maintained because the rudder deflection is maximum, or the pedal force is 150 pounds, or the aileron deflection is maximum, or the roll control force is the maximum defined. The heading change, by the way, is initially very slowly. The airspeed at which this occurs is VMCA wings level. In red, this first wings level test point. Then the test continues. This graph, made by the tail design engineer, was shown before. The bank angle is gradually increased to the bank angle for zero side slip as used for tail design, after which the airspeed can be further decreased until, with zero side slip, again one of the rudder and aileron limitations is reached. This is the static VMCA for thereafter, as was defined in the aviation regulation of VMC. This static VMCA is approximately 8 knots for a small twin and 30 knots for a 4-engine turbofan, lower than wings level VMCA. These 2 points are the only test points during flight testing to determine the static VMCA. But the aviation regulations require another test to be conducted, the dynamic VMCA test, during which the critical engine is suddenly made inoperative at decreasing airspeed test points. The aviation regulations require that the deviations from the flight path in yaw and roll must stay within certain limits, and an average pilot must be able to recover the airplane. The highest of static and dynamic VMCAs, which is usually the static, will be published in the airplane flight manual as the standardized VMCA of the airplane. This VMCA is always safe, even when the thrust is or is increased to maximum, provided straight flight with the 5 degrees of bank into the good engine is maintained. The VMCA definition in flight manuals and flying handbooks. This definition was already shown before and is in most cases copied from Design and Certification Regulations 23 and 25, paragraph 149. I will not read it again. Is this definition correct? Yes, but only for tail sizing, for certification and flight test, which is what Aviation Regulations 23 and 25 are for. This definition is definitely wrong for a flight manual, for a flying handbook, or a multi-engine rating textbook. There are several errors in this definition. I will discuss them with you. First is with an angle of bank of not more than 5 degrees. Does this mean that pilots have to keep the wings level to within 5 degrees either side to maintain straight flight while an engine is inoperative and the airspeed is VMCA? No, definitely not. The vertical tail is designed for and VMCA is determined and is only valid with a fixed small bank angle of 3 to 5 degrees away from the inoperative engine. The number of degrees depend on the airplane time. The not more than 5 degrees restriction is for the tail design engineer, for sizing the tail large enough to achieve zero side slip and limit the VMCA. This inappropriate copywork led, to my opinion, to many catastrophic accidents following the loss of control of performance, because the pilots did not maintain the favorable bank angle at low speed and high thrust. This inappropriate line is also copied to most, if not all, pilot textbooks and flying handbooks. Another error, the critical engine. I already explained that VMCA is determined while the critical engine is inoperative. But VMCA also applies after failure of any other engine, but is then actually a few knots lower though. Maybe even less than the difference between high and low weight. Therefore, critical does not belong in the VMCA definition for pilots. Critical engine never shows up in emergency procedures either. Now the last error, suddenly made. An engine fails or is inoperative. A pilot never makes an engine inoperative during normal operations. This condition is also for tail design and flight tests, as in Regulations 23 and 25. Suddenly made does not belong in the VMCA definition in flight manuals and textbooks for pilots. The published and indicated VMCA applies always, whether an engine suddenly fails or is inoperative. Good in this definition is, thereafter, maintain straight flight. But this was regrettably not noticed by many mishap pilots and accident investigators, because these pilots did not maintain straight flight with 5 degrees of bank angle away from the inoperative engine at airspeeds as low as or even higher than VMCA, because they turned to downwind for landing too early at too low a speed, or increased the thrust during the final turn for landing and got killed. Conclusion on this definition. This definition is for design, certification and flight test. It is not for pilots. It is copied inappropriately from design and certification aviation regulations. This definition is inadequate, even deficient for use in a flight manual and in flying handbooks. It is definitely inappropriate for use by pilots. Pilots learn the wrong technique to fly with an inoperative engine at low speed and high thrust setting. This definition does not help to stay alive with a dead engine. An improved VMCA definition for pilots would be: VMCA is the calibrated airspeed at which, when an engine fails or is inoperative, it is possible to maintain straight flight only, provided a small bank angle of 3 to 5 degrees, to be specified by the manufacturer, is maintained away from the inoperative engine when the thrust is maximal. I would add a warning: do not turn at airspeeds near VMCA while the thrust setting is high. Performance will and control might be lost, because some actual VMCA applies all the time when an engine is inoperative, including during the final turn for landing when an engine already failed during takeoff. Takeoff speed small twins. I repeat it once more: keeping the wings level increases VMCA to a higher actual value. The increase is approximately 8 knots for a small twin. The takeoff speed of small twins is required to be 1.05 times Vmca. This 5% safety margin is however not high enough. Since the wings are level at liftoff, it is recommended to use at least 1.05 Vmca plus 10 knots as a safe takeoff speed for a small twin. Ask the manufacturer of your airplane for the wings level Vmca so that you can add 5% safety margin to that speed. Following engine failure, attaining 5 degrees away from the inoperative engine should never be delayed, because bank angle is required for both performance and control. We'll now review the two accidents showed in the beginning again and show you what happened. Now the view from inside the cockpit from the left seat. The takeoff run starts. Everything looks alright. Rotation is at 75 knots, 16 knots below the takeoff speed of 91, 12 knots below the red line Vmca, and even 20 knots below actual wings level Vmca. Right after liftoff, engine number 2 failed at an airspeed of 82 knots below the red line Vmca. The loss of control was a fact. What went wrong on this accident? The published standardized Vmca in the flight manual was 87 knots. The regulatory takeoff speed would then be 5% higher, is 91 knots. The actual Vmca at rotation with the wings level is 87 plus approximately 8 knots, is 95 knots. The pilot rotated early at 75 knots, 16 knots below takeoff speed and 20 knots below the actual wings level Vmca. Way too early. The right non-critical engine failed at 82 knots, 5 knots below Vmca and even 13 knots below actual Vmca. The ailerons were either not maximum or not effective enough at too low a speed. There was an immediate loss of control by Vmca definition. It was not a stall. Takeoff speed with wings level should have been 1.05 times the wings level Vmca. That is 1.05 times 95 is 100 knots at least. This accident could have been prevented by delaying rotation until the airspeed was 100 knots and thereafter by maintaining straight flight with 5 degrees of bank into the good engine. Now the fatal accident with the Embraer 120. The rotation speed was 110 knots, which was as planned. Then the throttle number 1 was close to flight idle at liftoff for engine failure training, as we see on the instrument here. The yawing starts slowly at V2. There is no attempt to bank the airplane 5 degrees to the good engine side. The yawing increased even at V2, 112 knots. The airspeed decreased further down to 101, the rolling and yawing continued, and loss of control was a fact. What went wrong in this accident? The published standard Vmca was 97 knots, V2 was 113. The actual Vmca was 112 knots, because the video showed that the yawing started slowly. The actual Vmca was higher than the standardized Vmca because the 5 degrees of favorable bank angle into the good engine was not attained by the pilot. And because the throttle number 1 was closed, so propeller 1 did not auto-weather. In addition, the torque was not set for zero thrust, which increased the thrust yawing moment, both increasing the rudder requirement or required a higher airspeed. What the accident investigation report did not mention is that the yawing started while the indicated airspeed was V2. V2 was obviously not a safe takeoff speed. Takeoff speed V2 requires a favorable bank angle too. The indicated airspeed was allowed to decrease below both V2 and the actual VMCA, so the loss of control occurred by VMCA definition. The pilots and the accident investigators were not familiar with the true value of VMCA and the accompanying constraints. This accident could have been prevented by maintaining straight flight with a small bank angle into the good engine, even at takeoff safety speed V2. V2 on this airplane requires an increment to make it a safer takeoff safety speed. The following VMCA definition was found in the Flight Operations Manual of this airplane. VMCA is the minimum flight speed at which the aircraft is controllable with a maximum 5 degrees of bank towards the operative engine when one engine, critical engine, suddenly becomes inoperative with the remaining engine operating at takeoff power. The value presented represents the most critical combination of power, weight and center of gravity. In aircraft with auto-feathering, VMCA is calculated with a feathered propeller. A few remarks on this definition that should have been made by knowledgeable accident investigators. The airplane is not controllable with a maximum 5 degrees bank angle, but can only maintain straight flight at VMCA with maximum power setting. This is just the definition. VMCA is not for when one engine, the critical engine, suddenly becomes inoperative, but VMCA applies after failure of any one of the engines, critical or non-critical. VMCA is not calculated, but is determined, that is measured during flight test. VMCA is measured with the propeller in the position it assumes after engine failure. If equipped with an autofeather, that system is used, otherwise the propeller is windmilling. The last sentence should not be included in the definition, although it could be added that an inoperative autofeather system increases the actual VMCA. This definition, like most VMCA definitions in flight manuals, is definitely not correct for an airplane flight manual for pilots. This definition is not in agreement with design and flight test method and conditions and does not contribute to preventing catastrophic accidents as was shown here. A few do's and don'ts. Always delay rotation until the indicated airspeed is at least 10 knots higher than the takeoff speed. After engine failure, bank 5 degrees as soon as possible to the same side as the rudder pressure. Always maintain straight flight until reaching a safe altitude. Maybe that should be at least 1000 feet. When a turn is required, reduce the asymmetrical thrust and the rudder bit and make a shallow turn. You might lose some altitude because of the drag. When the rudder is near maximum, the actual VMCA and the loss of control are close. Increase your speed. Before increasing the thrust to maximum, when the airspeed is low, bank 5 degrees again into the good engine. During cruise with one engine inoperative, fly VYSE plus bank 2 to 3 degrees for minimum drag and for minimum descent. A long straight-in approach is much safer than increasing the thrust during the final turn for landing for maintaining the approach path. When the airspeed is low, never ever increase thrust to maximum without banking 5 degrees into the good engine first and thereafter maintain straight flight with that bank angle. Increase the rudder and the ailerons with the thrust. What next? If you still find all of this hard to believe because it's so different from what instructors taught you and from what is written in airplane flying handbooks, please refer to the formal FAA and EASA flight test guides, and to an online engine-out simulator of the University of North Dakota. Links are provided on the downloads page of my website for your convenience. If you are an instructor, accident investigator or textbook writer, I guess you'll have some work to do. If you need help, please do not hesitate to ask. You and I, we're all committed to improve aviation safety. We all want to return home safely after experiencing an engine failure, don't we? And so do our passengers. A great responsibility rests upon our shoulder. The necessary copyright statements, please pause the video to continue reading. The final question: can you prevent a dead engine from turning into a killing engine? Sure you can, but you should know and not forget about the air minimum control speed and respect it just like you do respect the stall speed of your airplane. Thanks for viewing this video. Please share with all pilots you know. Fly safely.